Hello and welcome to the Unit 6 Section 2 video on solving equations with nth roots and rational exponents. So in the last section we kind of got a little bit of an introduction to radical equations, that is equations that have a square root or a cube root. And here we're going to extend beyond that and go to nth roots, which just means we're talking about fourth roots, fifth roots, sixth roots, seventh roots, and so on and so forth, okay? Because they all basically behave the same way. So let's get a little bit of the introductory material out of the way first. When we're talking about nth roots, you can extend the concept to square roots to other types of roots. For example, 2 is a cube root of 8 because 2 to the third equals 8. Okay, here's a couple more examples. Square root of 16 equals 4 because 4 squared is 16. The cube root of 64 is 4 because 4 cubed is 64. This kind of goes back into the discussion that we touched on in the last section on inverse functions, okay? One function undoes what the other function does. An nth root of a is written as this, where you have the nth root, the n is being your index, a is what's under the radicand, or is your radicand, where n is the index of the radical and a is the radicand, okay? So you have that right there. Consider the following nth roots. Square root of 4 is plus or minus 2, because remember, 2 squared is 4, negative 2 squared is also 4, okay? So you have to account for both of those. We discussed that a couple of units ago. All right, the square root of negative 4 gives you two imaginary solutions. You have plus or minus 2i, because that I comes out of the square root, because the square root of negative 1 is I. Well, then if you go to a cube root of 8, the cube root of 8 is 2. Well, the cube root of negative 8 is negative 2. So we have two even indexed examples here, that being your square roots, and two odd indexed examples, those being your cubed roots, okay? So the first two are even indexed, and the bottom two are odd indexed. We can extend that to any even or odd index. It will hold all the way through, okay? So if you have an even index and what's under the square root, or what is your radicand, what's under the radical is positive, then you're going to have two real roots. That's like your first example there. Square root of 4 equals plus or minus 2. If what's under the square root or what's under the radical is negative, then you're going to have no real roots. You have two imaginary solutions, but no real roots, okay? If your index is odd, you're always going to have one real root. And if what's under the radicand or what's under the radical, your radicand is positive, then you have one real root that's positive. If what's under the radical is negative, then your one real root is going to be negative. So I think the odd index is fairly straightforward. You're going to have one answer. If what's under the radical is positive, your answer will be positive. If what's under it is negative, then your answer is going to be negative. And then we've done enough with the even indexed radicals that I believe that should be fairly straightforward as well. Two real roots if it's positive, no real roots if it's negative. All right, let's do some examples of these. And these are all fairly quick examples to do. We're going to find the real nth roots of a. Okay, so you're going to go here and you're going to figure out what your index and radicand are. So our index is odd in this one, and our radicand is negative. So since our index is odd and our radicand is negative, let's look at our table. We're odd, we're negative, so we should have one real root that's negative. So if we perform the math here, we have the third root, or the cube root of negative 216. You're going to end up with a negative value, and that happens to be 6. And you can use your calculator to help you find this information. But this is your index, this is what's under the radical, and so that's how it would be formatted. For B, we have an even index, and we have an A that is positive, so our radicand is positive. So how does this look? This is the fourth root of 81. Fourth root of 81, we would expect to have 2 real roots because it's positive. So we got plus or minus 3. And then for this one, the index again is even. The radicand again is positive. So we're going to take the fourth root of 625, and that's going to give us plus or minus 5. Because if you multiply 5 times 5 times 5 times 5, you'll get 625. Again, you can use your calculator to help you with this. All right, for D, our index is even, and our radicand is positive. So again, we're expecting 2 real solutions here. So the fourth root, or this time the sixth root of 64, well, that's going to give you plus or minus 2. For E, the index is odd. The radicand is negative. So when we take the cube root of negative 64, we would expect one negative answer, and that answer would be negative 4. And then finally, for this last one, the index is odd, the radicand is positive, so we would expect one positive solution. So when you take the fifth root of 243, you're going to end up getting 3. For this next set of examples, let's solve each equation taking the nth root, and we'll round the result to the 2 decimal places as needed. So let's start with A. The cube root of, well, x cubed is 64. If you want to undo a cube, you got to take the cube root. So we're going to take the cube root of x cubed, and if we do it to one side, we got to do it to the other, the cube root of 64. So we're going to end up with x equals 4. All right, for B, before we can take any roots, we need to divide each side by 4, because you got to isolate your x with its power first. So 128 divided by 4 is 32. And now we're going to take the fifth root of each side. And when you take the fifth root of 32, you know you're going to get one solution, and it's going to be positive. X equals 2. For C, before we can do anything, we need to multiply each side by 2 to get rid of the 1/2, so we can isolate our x to the fifth. So that's going to give us x to the fifth equals 10/24. And now we're going to take the fifth root of each side, like we did on the last one. And when we do that, we know we're going to end up with one positive solution, and that is 4. For D, our power is already on the outside, so we are going to take the fourth root of each side to get rid of that power. And when you take the fourth root of 21, since it's a fourth root, you know that you're going to have a positive and a negative. Okay, so we're going to put our plus or minus sign in front of that fourth root. Now, you can't break down the fourth root of 21 without a calculator. So you'll need to put that in your calculator, and you'll do that along with adding 3 or subtracting it from 3. Because when we pull 3 to the other side, you end up with 3 plus or minus the fourth root of 21. This is your exact answer. If you put it into your calculator, you can get an approximate answer. X equals, and remember, you're going to have 2 answers, 0.86 or 5.14. For E, similar setup here. You're going to take the fourth root of each side right off the start because there's nothing else you can do. Now the fourth root of 16 you can take. Now you know there's going to be a plus or minus. It's positive, so it will exist. So we're going to have x plus 5 equals plus or minus 2. And then we're going to move 5 to the other side, so you got negative 5 plus or minus 2. And that fairly easily breaks into your solutions of negative 7 and negative 3. On F, we're going to take the third root of x minus 2 to the third, and we'll do that to the other side. Third root of negative 14 is going to give us one negative answer, but we don't know what that is right offhand because the third root of 14 does not come out even. So we'll go ahead and just solve for x, get us to the end. So we've got 2 plus the cube root of negative 14. You notice this is not a plus or minus because this is not an even power. It's an odd power. So you're just adding 2 to each side. This is your exact answer. Your approximate answer is going to be x equals negative 0.41. Okay, now let's move on to simplifying radical expressions. So the properties of square roots also applies to nth roots. So we have a product property of roots where the nth root of AB is the same as the nth root of A times the nth root of B. And here you have an example of that. The quotient property also exists where you have the nth root of A over B equals the nth root of A over the nth root of B. And there's an example of this where you can break things up. Okay, to simplify the nth root of a power inside a radical, divide the power inside the radical by the index, okay? So if we have the fifth root of x to the 10th, then you're going to divide 10 divided by 5. That's going to give you 2, so your new power is going to be x to the 2nd. Okay? So we did 10 divided by 5, and that gave us 2. So let's try a few of these. We're going to simplify each radical expression. Well, this one we can break up because of our product property. Square root of 25 times the square root of x to the 4th. Square root of 25 is 5. And then the square root of x to the 4th, we have 4 divided by 2, because remember, there's always an imaginary 2 here when there's no number. 4 divided by 2 is 2, so you got 5x squared. For b, we're going to break this up. The cube root of 64 times the cube root of x to the 9th. The cube root of 64 is 4. And then when we do 9 divided by 3, we get x to the 3rd. For c, we have the 4th root of 81 times the 4th root of x to the 8th times the 4th root of y to the 4th. So the 4th root of 81 gives us 3. When we do 8 divided by 4, that gives us x squared. And then 4 divided by 4 gives us 1, so we have just y. Y to the 1st, we don't have to write the first power. Okay, for d, we have the 5th root of 32 times the 5th root of x to the 5th times the fifth root of y to the 15th times the fifth root of z to the 10th. So the fifth root of 32 is 2. X to the fifth, when you take the fifth root of x to the fifth, 5 divided by 5 is 1. 15 divided by 5 is 3. And 10 divided by 5 is 2. So you get 2x, y to the third, z to the second. For e, we're going to do the sixth root of 4096 times the sixth root of x to the 18th times the sixth root of y to the 24th. The sixth root of 4096 is 4. 18 divided by 6 is 3, so that gives us x to the third. 24 divided by 6 is 4, so that gives us y to the fourth. For this next one, we have the square root of 144 times the square root of x squared times the square root of y to the fourth times the square root of z to the 12th. And this breaks down into square root of 144 is 12. 2 divided by 2 is 1. 4 divided by 2 is 2. And 12 divided by 2 is 6. Moving on down to this next set of 2 rows. Just like we did before, we're going to break this up. So we have the square root of 16 times the square root of x to the fourth times the square root of y to the fifth times the square root of z to the 11th. So here, not everything's going to divide nice and even. Square root of 16 is fine. We've got 4. Square root of x to the fourth is x squared. 4 divided by 2 is 2. But then we get to where we have y to the fifth, we have 5 divided by 2. Well, we're going to break out everything that we can. So 1 power less than 5, the first thing that's the multiple is 4, okay? So in other words, 5 divided by 2 is 2 with a remainder of 1. Okay, remember going back and doing remainders when you first started division? We're going to use those remainders here. So y to the fifth, when you take the square root of it, we have 5 divided by 2. 5 divided by 2 is 2 with a remainder of 1. So the 2 comes out here, and then we'll have an y left over. Same thing for the z. Z to the 11th, square root of it, 11 divided by 2, you have z to the 5th with a remainder of 1z left over. So whatever variables were left over, those stay in your square root. So we had 1y left over and 1z left over. So those go in your square root. Let's try this with a cube root. So we've got the cube root of 27 times the cube root of x to the fifth times the cube root of y to the sixth times the cube root of z to the 12th. So the cube root of 27 is 3. X to the fifth, so 5 divided by 3 is 1 with 2 left over. So we're going to have a cube root with x squared left over in here. Then 6 divided by 3 is 2. And then 12 divided by 3 is 4. So the others work out nice and even. So we only have left the cube root of x squared. So I'm going to move this over so I can fit this in. So we're left with the cube root of, and let's kind of make it a little bit neater, kind of separate it a little bit so you know that 3 is not part of the exponent here. Cube root of x squared. All right, for I, the fourth root of 625 is 5. The x, we have 3 minus 3 divided by 4. That does not divide evenly. So you're going to have the fourth root of x to the third left over, at least. And then we've got y. 4 divided by 4 is 1, so just y to the first. And then 20 divided by 4 is 5, so you have z to the fifth. And so you end up with 5y z to the fifth times the fourth root of x to the third. For the next one, square root of 12, well, that does not come out even. So we're going to have to break that into the square root of 4 times 3 so we can pull something out of that. We're going to have the square root of x to the third. We're going to have the square root of z to the 10th. Well, we end up with 2 from here. We can pull an x out with one x left over, and we can do all of our z's. Get z to the fifth. So what we're left with in the square root is going to be 3 and our x that's left over. For k, cube root of 16 does not come out even, so we're going to have the cube root of 8 times 2, because 8 is a cube, times the cube root of x squared, times the cube root of y to the fourth. Let me make that a little bit nicer. Times the cube root of z to the 14th. All right, so the cube root of 8 is 2. We're going to have the cube root of 2 left over. Let's see what else we're going to have. We have an x, but there's no, it's 1 divided by 3, so we're not going to have anything left over, anything we can pull out. So we're going to have the x left in here. Actually, it's x squared, but still going to be left over. And then we have y to the fourth. So 4 divided by 3 is 1y with a y left over. And then 14, z to the 14th. 14 divided by 3 is 4. So you got z to the fourth. And you're going to have 2 z's left over. And then finally, for this last example, for L, we have the fifth root of 32 times the fifth root of x to the 10th times the fifth root of y to the 7th times the fifth root of z. Well, the fifth root of 32 just happens to be 2. X, we've got 10 divided by 5, that's going to be x squared. 7 divided by 5 is 1 with 2 left over, so we're going to have a y squared left in this fifth root. And then we've got the z left over in the fifth root as well, because 1 divided by 5, you don't have anything coming out, you've got that z left over. So it is important to kind of get familiar with how to simplify these radical expressions, because you're going to need that moving forward as we move into solving equations. And now we're going to talk about an easier way to look at it, and that's through rational exponents. So, a rational exponent is an exponent that can be expressed as m over n, where m and n are integers. So basically, we're expressing the exponent as a fraction. So the exponent 1 over n indicates the nth root. So here's a formula for that. A to the 1 over n equals the nth root of a. So for example, 16 to the 1/4 is the fourth root of 16, which would be 2. The exponent m over n indicates the nth root raised to the nth power. So a to the m over n is the same as the nth root of a raised to the m, or you can say it as the nth root of a to the m. So 8 to the 2/3 would be the same thing as the cube root of 8 raised to the second, which is 2 squared, which is 4. Okay, it's important to understand how rational exponents are radicals, especially when solving equations. Remember that a radical with an even index results in 2 solutions. So let's do a few examples of this. Let's rewrite each expression as a radical and we'll evaluate it. So 9 to the 3 halves, that's going to be the same as saying the square root of 9 raised to the third. Well, the square root of 9 is 3. So 3 to the third gives you 27. 64 to the 1/3. Well, that's going to be the same as saying the cube root of 64. And really, it's the cube root of 64 all raised to the 1, but you don't have to raise it to the first power. So the cube root of 64 is 4. 16 to the 3/4 is the same as saying the fourth root of 16 raised to the third. Well, the fourth root of 16 is 2. So 2 to the third gives us 8. 27 to the 2/3, that's the same as saying the cube root of 27 raised to the second power. The cube root of 27 is 3. And 3 squared gives us 9. 81 to the 1/4, that's the same as saying the fourth root of 81. And that is 3. And then 36 to the 5 halves is the same as saying the square root of 36 raised to the fifth. Well, the square root of 36 is 6, and 6 to the fifth gives you 7,776. And yes, you can use your calculator to find that if you would like. Now, rational exponents have the same properties as integer exponents. So I have listed for you on the rest of this page all of those rules that you learned way back in Unit 0. So all of these were just copied and pasted from the Unit 0 notes, and specifically Section 0.3. So if you want more information on these particular rules, product rule, power of a power, power of a product, quotient rule, we go on down to power of a quotient, the zero exponent, and the negative exponent. If you want more information on how all those rules work, go back to your Section 3 of Unit 0 notes. Go back to that video and you can see my explanations of these rules. Okay? We have already covered all those rules, so I am not going to spend the time covering those rules again here. But we are going to get some practice using them. So let's simplify each expression using the properties of exponents. So this is not nearly as bad as you think it looks, okay? I know it looks complicated because we have exponents that are fractions, and I know how you feel about fractions. But hang with me here, it's not as bad as it looks. So for A here, we're just simplifying, okay? You can take your coefficients, this 3 and this 4, and you can multiply those separately. And then we're going to take care of our x's. How do we multiply things with the same base, but different exponents? You're going to add the exponents. So you got x to the 1/2 plus 5/3. Okay? Now, 3 times 4 gives us 12. We can go ahead and write that part. But for the x part, with these exponents, you got to find a common denominator. And that common denominator is 6. So 1/2 is 3/6. 5/3 is the same as saying 10/6. Okay? Once you have a common denominator, add those exponents. So you've got 12x to the 13 over 6. That's it. Once you've combined everything, you're done. Let's try another one. B. We're going to pull our coefficients out on their own, and we're going to do our x's together. X to the 2, and we're adding the exponents, but there's a minus sign here, so it's going to be 2 minus 4/3. Again, we have to find a common denominator. This one's a little bit easier. We'll go ahead and put our 6 there. This one, we're going to do x. We only need to do something with the 2, and that's the same as saying 6/3. So x to the 6/3 minus 4/3, that's going to give us 6x to the 2/3 once you subtract those exponents. For C, again, we are going to multiply our coefficients on their own. Now we're going to do our x's together. So we got x to the first plus x to the 3/4. So we've got 1 plus 3/4. And then we've got y to the 5/4 times y to the 4/3. So we got 5/4 plus 4/3. So let's go ahead and multiply 4 times 4. That's 16. We got to find common denominators for both our x and our y. Well, this one's easy. We just got 4/4 plus 3/4. For your y, our common denominator is going to be 12. So this becomes 15 over 12 plus this is going to become 16 over 12. And so we have 16x to the 7/4, y to the 31 over 12. And that's as good as it's going to get. All right, let's move on down to D. Again, let's take care of our coefficients first. 2 times 3 times 3. And then let's do our x's. We got x to the 2 plus 2 plus 1/3. And then you've got y to the 3/2 plus 3/2. So when you evaluate that, 2 times 3 times 3 is going to give you 18, because 2 times 3 is 6. 6 times 3 is 18. We got to get a common denominator for the x's. And that's fairly straightforward. X to the 6/3 plus 6/3 plus 1/3. And then you have already a common denominator for your y's. So we'll go ahead and add those. 3/2 plus 3/2 is 6/2. And then we finally add our x's. So we got 6/3 plus 6/3, which is 12/3, plus another third is 13/3. So x to the 13/3. And then 6 divided by 2 gives you y to the 3rd. All right, let's check out E. Now we're doing power to a power. This is even easier because when you do power to a power, you multiply the powers. So you're going to have x to the 3/2 times 5/4. And when you multiply fractions, you just multiply across. 3 times 5 is 15. 2 times 4 is 8. So you have x to the 15/8. For F, we have x to the negative 3/2 squared. So we're going to multiply those powers. So you've got negative 3/2 times 2, which that gives us x to the negative 3. And then to write it in the simplest form, we don't want negative exponents, 1 over x to the 3rd. Let's move on down to G. So this one, we've got an x and a y. Still going to behave the same way. You're just going to multiply both of these exponents by the power on the outside. We did simpler versions of these back in Unit 0. So for this one, you've got x to the 2/3 times 3/2, y to the 3/4 times 3/2. So that's going to give you x, because 2/3 times 3/2 gives you 1. And then this one, you've got 9 over 8 for your exponent. So y to the 9/8. For h, similar setup. We've got to do x to the 1 times 1/3. So you're just going to have x to the 1/3. Y to the 1/2 times 1/3. So you're going to end up with x to the 1/3, y to the 1/6. For I, well, this one we're dividing. So let's go ahead and do our coefficients first. We've got 4 divided by 4. And then let's take care of our m. When we divide, we subtract exponents. So it's going to be 2 minus -3/4. And that's going to give us 4 over 4 is 1. So we're going to have m. Let's go ahead and get a common denominator. M to the 8/4 plus 3/4, which gives us m to the 8 plus 3 is 11, m to the 11/4. For j, we have 6 over 2, and then we have x to the -3/2 plus, or I should say minus, because we are dividing, minus 3/2. 6 over 2 gives us 3. -3/2 minus another 3/2 gives us x to the -6/2, which gives us 3x to the -3, which can be written as 3 over x cubed. For k, we only have the one coefficient, that's 3. Then we have x to the 5/4 minus 1/2, y to the 1/2 minus 1/2. So we end up with 3x, we need to get a common denominator here, 5/4 minus 2/4. Y to the 1/2 minus 1/2 gives us y to the 0. But of course we know anything to the 0 power is just 1. So we end up with 3x to the 5 minus 2, which is 3/4. And then finally for L, we have 12 divided by 3, x to the 2/3 minus 1/4, and that's a 1. Let me clean that up for you. So that is a 1. And then y to the 3/2 minus 3/2. So 12 divided by 3 gives us 4. We got to get a common denominator for our x's, so that common denominator will be 12. So we'll have x to the 8/12 minus 3/12. And then y to the 3/2 minus 3/2, that gives us y to the 0 again. Anything to the 0 power gives us 1, so we end up with 4x to the 5/12. So I know this is a lot of examples, but this is basically just going through those power rules. I know we're dealing with fractions. Sometimes you have to find a common denominator, but it's nothing that is extremely difficult. Okay, let's move on to the final item for this section. So now we're going to solve radical equations. We have gotten all the practice we need for simplifying and what all of our power rules are, and we've done all the pieces. Now we're going to put it together to actually solve some equations. So when an equation contains a power with a rational exponent, you can solve the equation by first isolating the power, then raising each side of the equation to the reciprocal of the rational exponent. So for example, if you have x to the 1/2, you can get rid of that 1/2 power by raising it to the second, because we multiply those exponents. X to the 1/2 times 2 over 1 gives us just x. So let's solve a few equations and show you how this works. So let's start off with A. We have p to the 4/3 plus 1 equals 82. First thing you got to do is isolate your variable. So that we do that by subtracting 1 from each side. And when we do that, we get p to the 4/3 equals 81. Now we're going to raise p to the 4/3 to the 3/4 power. That's the reciprocal. And if we do it to that side, we have to do it to this side. Okay? Now, remember, the bottom number in your rational exponent is your index. Okay, so this is like saying we're taking the 4th root of 81 to the 3rd. Okay? Since this is an even index, we are going to have a plus or minus on our answer. And this is like saying the 4th root of 81 to the 3rd. Okay, or in other words, the 4th root of 81 taken to the 3rd, because I think finding the 4th root first is going to be easier. The 4th root of 81 is 3. You can use your calculator to find that. And then 3 to the 3rd power gives us 27. So p is plus or minus 27. And that's it. We solved for p. Let's try b here. Okay? So we've got 3x to the 2/3 equals 375. First, we've got to isolate our x to the 2/3. So we divide each side by 3, and that gives us 125 on the right-hand side. Now we're going to take x to the 2/3 to the 3/2 power. That's the reciprocal of our 2/3. And if we do it to that side, we have to do it to the other, to the 3/2. Okay, so now we have x equals the square root of 125 to the 3rd, or I think it's going to be easier to do it the other way. We'll do the square root of 125 to the 3rd. Well, as it turns out, this is not going to work out nice and neat because we cannot take the square root of 125. So you're going to end up getting an approximated answer doing this. And as it turns out, I have an error in your notes. So let's address that, okay? So just like in class, sometimes we find an error in the notes as we go along. So we're going to change this problem to be x to the 3/2, okay? So instead of 2/3, we're going to make this x to the 3/2. So again, we're going to divide each side by 3, okay? So that part doesn't change. We still get 125. But now we are going to have x to the 3/2 taken to the 2/3 power. Same thing for this side. Okay, so we end up with x equaling what is essentially the cube root of 125 squared. This we can actually do. The cube root of 125 is 5. So you end up with 5 squared. 5 squared is 25. So your answer for this one is 25. I apologize for that error that I had in the original problem there. It should have been x to the 3/2. But this is math. Sometimes we run into a block and we find where the problem is and we readjust. Okay? It's just part of problem solving. Okay, so let's go on to the next one. The next one is correct in the way that it is structured here. So let's see what we have for this one. So x plus 3 to the 5 halves. We are going to take each side to the 2/5. There's nothing that we have to do to isolate it. It's already by itself. So we're going to take this to the 2/5 on this side, which means you have to take 32 to the 2/5. So when we do 32 to the 2/5, and at this point, I would recommend that you just put it in your calculator that way. Okay? Don't make this more complicated than it has to be. You can put into your calculator 32 to the 2/5. Now just be aware, when you do 32 and then the caret symbol, so let me write it right here. When you do 32 and then the caret symbol, you need to put in parentheses the 2/5 when you put it in your calculator, okay? Otherwise, you'll end up doing 32 squared divided by 5. So when you do rational exponents in your calculator, which you can do, make sure that rational exponent is in parentheses. So if you put in 32 to the 2/5 in your calculator, you end up with 4. And then subtract 3 from each side, x equals 1. I think using your calculator, because you will be allowed to use that on your tests and on your assignments and whatever else you need to do, I think that is going to be the way to go in doing some of these quickly and easily, okay? All right, for the D, let's isolate the part that's got the power. So we've got x plus 2 to the 2/3, and we're going to subtract 3 from each side. So we've got equals 4 on the right-hand side. Now we're going to take our x plus 2 to the 2/3, and we're going to raise that to the 3 halves, which is the reciprocal, and we've got to do it to the 4 as well. Okay? Again, put 4 to the 3 halves in your calculator. On this side we have x plus 2. You put that right-hand side in your calculator, you get 8, but remember, this is an even index. That bottom number of your rational exponent gives you an even, tells you it's an even index, which means you're going to have a plus or minus 8, okay? So make sure that you pay attention to the even index. And refer to that table on the first page of your notes as you need, as you practice these. And so we're going to have x equals -2 plus or minus 8, and that's going to give us our two answers, which will be x equals 6 and -10. All right, let's do these last two examples. So we'll isolate the x plus 2 to the 3/4 first. We add 1 to each side, that gives us 8. Now we're going to take x plus 2 to the 3/4 and raise it to the 4/3, which is the reciprocal. We do the same to the 8. That goes to the 4/3. So on the left-hand side, we get x plus 2. You put 8 to the 4/3 in your calculator, you're going to get 16. And so x equals 14. And then our final example, we're already isolated, so we're going to take -5 minus 3x to the 3 halves, and we're going to raise it to the 2/3. We're also going to raise 343 to the 2/3. So the left-hand side, your powers cancel each other. You get -5 minus 3x. On the right-hand side, you're going to have 49 when you put that in your calculator. Then, from here, it's just solving. Add 5 to each side. You get 54 on the right-hand side. And then divide by -3, and you get x equals -18. And there you go. So nothing really too complicated. Once you get the power by itself, you raise each side to the reciprocal of that power, and you are good. All right, so this concludes section 2 of Unit 6. There's only one section left, and that is looking at some practical applications of this and real-world applications. So we'll be doing that in the next section.